Hello everyone, I'm Kai Lai of National Taiwan University. Today I'm presenting an extended version of my master thesis entitled String a Tree in Near Linear Time. This is a joint work with my master thesis advisor, Professor Liu, and our friend, Professor Torup of University of Copenhagen. And this is our outline. The string a tree problem is that given a simple graph G and 3 vertices of G, output an yes/no answer to whether G contains an induced subgraph that is a tree that contains the 3 specified vertices, or terminals. We may assume that the terminals are the leaves of G, without loss of genericity. The previous work is that Chudnovsky and Seymour gave the previously only known polynomial algorithm that runs in mn² time, and their algorithm relies on a characterization of graphs that does not contain a string tree, and they use a classic decomposition method. Our contributions in graph theory is that we gave a new stronger characterization for graphs that does not contain such a tree. Also, as a byproduct, we gave a self-contained shorter proof for their original characterization. From the algorithmic point of view, we gave a near linear algorithm for the string tree problem, and gave faster algorithms for recognizing perfect graphs and detecting several other types of induced subgraphs. Such as the table showed, we improved the algorithm for detecting the pyramids, the thetas, the beetles, the odd holes, and the even holes. All of the algorithms here uses the string tree as a subroutine, but also contains many bottlenecks. Let's start from the graph theory. For simplicity, let a sapling be an induced tree that contains all 3 given terminals. The Chudnovsky and Seymour characterization says that G is sapling free if and only if G emits a local net decomposition. We will introduce it very fast because in our characterization we also use the net structure. For a subset X, we partition X into a subsets called arcs and nodes, and in particular, the arcs form a disjoint partition of X. And let H be a graph with each member of EH an arc and each member of VH a node. If certain condition holds, then the subgraph H of G induced on X is sapling free, and we will call H an XNet of G. Let's look at some examples. This graph here is clearly sapling free because any induced subgraph that contains these 3 terminals will have to contain the triangle here. And the XNet, the net structure looks like this, with the light gray ones, the arcs, and the dark gray ones, the nodes. Notice that if we add a connected component like this, that is sort of local in the sense that all its neighbor is contained by this arc here, then the graph is still sapling free. And if we add a vertex like this, the same arguments hold. The graph here is also sapling free. To see that, we can partition it like this. And let's start from the terminal here and try to span a tree that reaches the other. When we walk to this node here, we can either go left or right, but not both, since otherwise the induced subgraph will contain a triangle. Suppose that we go left. When we reach this node here, we face a similar situation, and we can go either left or go right, but not both. Consequently, the graph is sapling free. Also, if we add a connected component that is local like this, or a vertex here that is local, then the same argument hold. So the formal definition of a net is as follows, that the arcs form a disjoint partition of X, and H has exactly 3 leaves. Each of them contains a distinct terminal of G. And the room condition says that for each vertex X in G contained by an arc, there is an induced path that joins the two end node of E that contains X. For example, the vertex 10 is contained by E2, and the path A10 to here contains 10 and joins the two end node of E. The adjacency condition says that an arc and a node have non-empty intersection if and only if they are incident. The separation condition says that for any vertices U and V contained by distinct arcs E and F of H, UV is adjacent if and only if E and F share common end node V that contains U and V. And the subset of K is outside of X is local if all the neighbors of K contained by X is contained by an arc, a node, or a child of H. So the vertex 5 here is local, and vertex 4 here is non-local. And the XNet is said to be local if all the connected components of G minus X are H local. And our stronger characterization says that G is safely free if and only if G emits a web decomposition with a local ID net. And the web is just a net that allows parallel arc, such that each arc is either simple or flexible. And the ID net is an XNet that describes the outlook of the web edge. And the role of H star is similar to the original characterization. Roughly speaking, the web stores the fine-grained information within each arc, and the ID net stores the coarse-grained structure and gives us more control over G minus X. The merging operation is very important during our paper. Let UV be a cut set of H, and let C be a connected component of H minus UV, like the two nodes here. Then we can merge the arcs of the graph here into a bigger arc, UV, while preserving the net property. In reality, the definition won't work because H might contain a cut vertex, so we must add 3 dummy arcs between each pair of leaves of H, and the resulting graph, say nabla H, will be biconnected. And we define a split pair, UV, to be either a non-dummy arc of nabla H or a cut set of nabla H. And we define a split component similarly as the previous slide, but on split pair and on the nabla edge. Also, we request that a split component does not contain a dummy arc, so it is a subgraph of H. Roughly speaking, a split component is something that we can merge while preserving the net property. And the ID net H star is obtained by merging every maximal split components of the web edge. For example, the E2, E3 to E8 here is a maximal split component, and we can merge it to an arc here, E2 table, and do a similar thing here to obtain the ID net. Notice that the maximal split components are uniquely determined by the leaves of H, so the ID net is also unique. Recall that a web is a net that allows parallel arc such that each arc is either simple or flexible. And the arc E is simple if G induced on E is an induced path. And E is flexible for every subset S of E, GE contains an SUV route, which is something that looks like this, or something look like this. or something look like this, where the yellow vertices belongs to S. And the intuition of a sprout is that suppose that we have a minimally non-edge star local path here, and let S to be the neighbors of one of the endpoint neighbor in E. Then the sprout helps us join the two end node of E, like this or like this. Consequently, if G induced on X cup Y does contain a sibling, then the sprout and the non-local path here will be part of the sibling. That is, the end vertex will join to one terminal, and the vertex here joins to one terminal, and the vertex here join to one terminal. And we use this a stronger inductive hypothesis to lead to a simpler induction step. And our proof is self-contained and implies the Chudnovsky and Seymour characterization. Now let's talk about the algorithm. The Chudnovsky and Seymour's algorithm is very simple, that we first find a base extent of H, like this, by the shortest path algorithm. Then we will find the candidate path in G minus X, which is minimally non-edge local. Then we will try to extend the net structure like this, or we fail to do so, so a sibling was found, like this. We will repeat the process until there is no candidate anymore, and the net structure becomes local, and G is sibling free. They uses a subdivision and join operation, which we also used in our algorithm, that works like follows. Let U be an endpoint of a candidate Y like this, and suppose that U is E local for an arc like this, and there is an induced path P that intersects the neighbors of U in exactly two adjacent vertices. Then we can remove the other vertices from E like this and do a subdivision on E. Also, we will do a similar thing to the other endpoint of Y here. So the resulting graph looks like this. And the other example, the other case is that U is V local to a node V, and U is adjacent to all the vertices contained by V. In which case, we can simply put U into V and do a similar thing here, a subdivision, and join the new arc like this. Our algorithm follows a similar flow that we first find a base X web H and its ID net H star. Then, in each iteration, we find a candidate path that is minimally non-H star local. Then, we will either extend the web structure and update the ID net correspondingly, or we will find a sibling. We will repeat the process until there's no candidate can be found, and the ID net becomes local, and G has no sibling. The first big ON factor was removed by our stronger characterization, that in step 3, we can extend the web to an X cup Y web, that is, without removing any vertices out from the web structure. So the size of the web is strictly increasing, and we can bound the iterations by n. While in the previous algorithm, a potential function was used to bound the number of iterations by n squared. And we extend the web by the pod. That is, for a candidate Y, a pod is a minimal split component that is sort of contains the neighbors of Y in X. Something look like this. And we can merge the arcs of this minimal split component of the pod and put the Y into the new arc. The new arc is guaranteed to be flexible, and therefore the result will be a web. Also, if y emits no path, then G induced on x cup y contains a sapling. Notice that in the old algorithm, we might do a subdivision on this arc and remove some vertices out from this arc. Another big O(n), nearly big O(n) factor was removed by the dynamic data structures, including top trees and SPQR tree. And actually, the split components of the web allows a sort of partial order that was described by the SPQR tree very well. Therefore, we will maintain an SPQR tree over the web edge and uses a dynamic algorithm to support our operations of merge, subdividing, and join. To find the maximal split components to compute the ID net, and to find the minimal split components to find the part of y, of a candidate y. And we use the top tree to find a candidate. Suppose that each arc and node are assigned a unique color, and then a local vertex is just a vertex in G minus X that has a few good adjacent colors. And the candidate is just a minimal path that contains many bad adjacent colors. And the top tree is a data structure that is particularly useful in finding the minimal paths in trees. So we will maintain a spanning forest over the G minus X and maintain a top tree over each spanning tree in F. And we will use a modified dynamic top tree algorithm to store the adjacent color information and support the operations of merge, subdividing, and join. Now let's talk about the perfect graph. A graph G is perfect if every induced subgraph H of G satisfies that the chromatic number of G equals the size of maximal clique of G. And the famous strong perfect graph theorem says that G is perfect if and only if G is purged. That is, neither G nor the complement of G contains an odd hole, where an odd hole is just an induced cycle with odd lengths greater than 3. And Chudnovsky, etc., showed an n⁻⁹ time algorithm for detecting the perfect graph, and we improved it to n⁸ which is n⁶ times the time to do the matrix multiplication. And detecting odd hole has been an open problem for a very long time, until recently solved by Chudnovsky, Seymour, Scott, and Spergel, and they gave an n⁹ time algorithm. And one of their 7 bottlenecks is detecting pyramids, which is improved by our Stronger tree algorithm. And we also improved the other 6 bottlenecks to m² n⁴ time. And by the strong perfect graph theorem, this is also an improved algorithm for perfect graph recognition. And it will be nice to know that whether the Stronger tree problem can be solved in real linear time. Thanks for listening. Have a nice day.